Hi everyone, this is Ken DeLong, author of the Economic Comic, and today I want to talk to you about something pretty wonky, the equation of production. So the equation of production is a mathematical equation that economists use to model the economy and describe the economy and predict things about the economy. And I want to go through the way the equation of production is usually handled. I want to talk to you about why I think that's all nonsense, and then try to give you a better sense of what a real model of the economy might look like and why it's ludicrously complex and completely different from what modern economists use. So this is the equation of production. Q equals function of L and K. What does that mean? Uh, Q is the total output of the economy, and it's just saying it's a function of L and K, where L is the aggregate labor supply and K is the aggregate capital stock, right? So basically all the people that can work and all the tools they have to work with, and there's some function F that you can combine them up and that produces some amount of output. So yeah, I guess we all knew that, right? Like the more people you have, the more stuff you can make, the more factories you have, the more stuff you can make. Um, the real uh, juice here is in the shape of F, right? Like what is F? F can be anything. And that's the most interesting part. Here's one of the, like the, probably the most simple version of that would be what they call the Cobb-Douglass production function, where the output is just equal to some constant A, some constant of proportionality, you can ignore that, times labor to the 1 minus A and capital to the A, where the little a goes from 0 to 1. So basically this is saying you can get the same amount of output from a lot of labor with a little bit of machinery, or a lot of machinery with a little bit of labor. In other words, you can take 1,000 guys with shovels and they can move the same amount of dirt as 10 guys with bulldozers. Okay, yeah, kind of knew that. I'm not sure this gives a lot more insight, but let's talk about what's wrong with these equations. Okay, first let's talk about some mathematical models. So first of all, I'm a physicist. Part of my training is to look at the real world and build mathematical models of it. Now, why do we do that? Well, if we can get a good mathematical model of the world, we can do things and like basically almost run experiments that you can't do in the real world. For example, if I had a great model of how the sun works and I turned the temperature way down, I could find out what happens in the sun, what I think would happen in the sun if the temperature went down. I can't actually go to the real sun and turn the temperature down, right? But if I have models that I think really truly describe what's going on there, I can use the equations to kind of say, well, as the sun gets cooler, here's what's going to happen, right? Now, once you start learning this stuff, you find out that you can't model anything, right? The real world is extraordinarily complex, and even the simplest systems defy a good mathematical description. So you need to make simplifications. And what I'm going to argue here is that the simplifications that economists have made for the equation of production are garbage. So if you were my grad student and you came to me and said, here's my model of the economy, and you presented those equations, I would fail you, right? So let's talk about why. Okay, so in the next few slides, I'm going to go through why I think those equations are missing very, very important pieces of the economy that can't be abstracted away, and how we might want to model it. We'll develop some new equations, but don't freak out. First of all, these equations are not going to be perfectly correct. I don't do this kind of work anymore. It's been a long time since I've done this detailed of mathematical modeling, so I know it's messed up. And also, it doesn't even matter if you understand what I'm writing down or not. I just want to express to you the complexity of the economy. All right, so mathematicians out there and economists, like, don't freak out over my equations. Take them as sort of illustrative rather than definitive. All right, so let's start with the variables. Aggregate capital, aggregate labor, aggregate output. What in the world does this mean? So first of all, let's examine in the real world, what is capital? Well, a machine that picks tobacco leaves, right? A cloud computing data center, that's capital. A fishing boat. Okay, how do you aggregate those? How do you add them all up? That seems almost nonsensical, right? If you have, now, generally what economists will say, modern economists will say, well, you look at their prices and you add the prices together. But obviously, if you had $10 million of cloud computing equipment, $10 million of fishing boats, or $10 million of tobacco leaf harvesting equipment, you have a very different economy, right? Like those are not interchangeable things. Another thing to think about here, what I think looks to me like a fallacy is that let's take this tobacco harvester. Let's suppose it costs, I don't know, $50,000 and there's 1,000 of them in the economy. Then we say, okay, that's $50 million worth of capital. I think that's wrong on several counts. On one count, um, you can't, when you say the cost of a tobacco harvester is $50,000, that means like you can go out and buy one for 50,000. So it's what we call the marginal cost, right? Given the fact that there's already 1,000 out there, if you go to the store and buy one more, the 1,001st one, they charge you 50,000. But if there were only two harvesters out there and you went to buy the third one, it will cost way, way more than that because there would be this huge unmet demand for tobacco, right? If we can profitably use 1,000 of them, but there's only two, the third one, increases production by 50% and it would be massively valuable. So they'd be able to charge way more than $50,000 for it. So the point is that you can't take the marginal cost of a tobacco harvester at 50,000 and just multiply by the number that are in the economy. That doesn't accurately capture the value of those things, right? And while we're talking about value, um, let's say we bought all these tobacco harvesters last year, we bought $50 million worth. But then last night on TV, there was a movie that was heart-rending and heart-rending and got everybody to stop smoking. Everybody woke up this morning and said, I am not going to smoke anymore. And they just all quit cold turkey. All right, well, how much are your tobacco harvesters worth now? Right, they're not worth anything. There's nobody wants tobacco anymore. So these machines that are specialized to harvest tobacco are certainly not worth $50,000 anymore. Maybe there's a scrap, salvage value there, or you can melt down some of that steel. I don't know. Um, so simply looking at the purchase price of capital equipment that was paid in the past and multiplying it by the number of existing units, it's just not valid, right? It's not a good model of the actual world. But let's keep going. Here's some more assumptions that economists will make. So they'll say, let's look at the year n. So these little n's and n plus ones, those are the year. So here we are in year n, let's say year number one, whatever. And the output of the economy Q gets split up. Some of it we consume, that's capital C, and some of it we save and invest, so that's capital S. So what does it mean to save and invest? You buy more capital equipment, right? You put it into investment. And so next year's capital, K of n plus 1, is equal to this year's capital plus everything we save. Right? Well, again, this is nonsense because as we saw on the previous slide, like there's multiple different types of capital. So I'll give you an example here that I just lifted from the great economist Bob Murphy, who I first heard use this example. Let's say we took all our savings and investment from this year, all of S sub n, and we bought hammers. And we just manufactured like 1 million new hammers, right? Wouldn't that be great? Now we have all this extra capital. Let's go and just add it to the aggregate capital stock. But if we didn't make any more nails, those hammers aren't worth anything, right? It's malinvestment. It's bad production. It's basically junk. Maybe we can put them in a box for a couple decades until we need them, but they'll probably all rust away and be worth completely nothing. So you can't just say you take this year's savings and investment and add it to the capital stock because it totally depends on the structure of the capital. Like hammers, the number of hammers and the number of nails have something to do with each other. The number of fishing boats and the number of outboard motors has something to do with each other. Like you can't just increase the capital blindly without understanding how it relates to each other, right? And that's nowhere captured in these equations. Again, as a modeler, I would say, oh, okay, that's clearly, like looking at the hammer and nail example, this is a really important example. And so I need to include that in my equations, but it's not here. We just have capital K, which is the sum of all capital. Nonsense. All right, let's talk about capital L, aggregate labor. Let's use an example. Let's look at several different types of labor. So, stenographer, someone who's a fisherman, someone who's a biologist. can you add those together, right? If next year we increase the labor supply by 10 stenographers, is that the same as increasing it by 10 fishermen? Is that the same as increasing it by 10 biologists? Or even if you add their salaries or whatever it is you want to do, like it doesn't make sense. Again, the economy is very, very, very different depending on what the combination is. You need to take into account these different types of disparate types of labor. Let me give you another example if you don't agree. So, and with this one, we'll look a little bit at the concept of like, okay, like in the Cobb-Douglass equations, they just took labor times capital, with some scaling function, some exponential function, and said, okay, if you double labor, you get double output. You double capital, you get double output. Again, I think that's complete nonsense. Let's take a look at an example. Let's look at some forms of labor. Let's say we have someone who designs applications, all right? Then we have someone who's a product manager, and then we have someone who's an iPhone developer and someone who's a back-end database and cloud engineer. All right? These four people together as a team can produce a kick-ass iPhone app, right? They could really produce a blockbuster with this skill set if they're all good and they all work together and they do a good job, and if they have the right capital. So the app designer needs some kind of design software so she can prototype different screen flows and layouts and storyboards and things like that and understand what the app, conceive of what the app would look like. The product manager is using spreadsheets and Word docs to manage all the requirements and the progress, the timeline, the budgets and things like that. That's all really necessary. The iPhone developer uses some software called Xcode, which allows him to write iPhone's apps. And the backend engineer is going to be using some cloud computing infrastructure and databases and some other software to do her job. All right, so we have all this labor, we have all this capital. If it's matched up like this, my contention is that this aggregate L and aggregate K could do a lot of good. They could produce a lot of good value for the economy. But let's just do this. Let's switch them up, right? Suppose we have the app designer working on the database and the cloud computing infrastructure. The product manager is writing all the iPhone code. The iPhone developer is managing the product with spreadsheets and Word documents and issue trackers. And the cloud engineer is doing the design of what the look and feel of the application. All right, if you do this, the output of this configuration is going to be quite literally 1,000 times less than the other one. If they actually managed to produce anything at all, which is kind of unlikely, it would be a piece of crap, right? It would be nothing like what they would do in the other configuration. Same aggregate labor, same aggregate capital, right? But just by rearranging it, you change the output of this little microeconomy here by orders of magnitude, right? So if you have something that big, you need to account for this effect in your equations. So one of the big things that's missing in the equation of production is heterogeneity, is that there's more than one type of labor. People are not just interchangeable objects that carry a unit of labor that can be applied to anything. There's more than one type of capital. Machines are not interchangeable. You can't just hand one unit of capital to the random person and get the same output out of them, right? Which person uses which machine, or let's say does which job, is incredibly important and will change the output of the system by many orders of magnitude. So in order to capture this diversity, what's the first thing we have to do? Well, we have to break these aggregates up. So we're going to take aggregate labor, L, and we're going to change that into basically from a scalar to a vector, if you know any math, if you know what that means. So now there's an L for each person. The subscript I represents which person. And if we're thinking about, let's say, the United States, I goes from 1 to, 330 million, right? So there's 330 million L's now, one for each person. And then K, the aggregate capital, is broken up into the different types of capital or tools that we use to do our jobs. And that's denoted by J. And I have no idea how many different types there are. I suspect it's more than the number of people. So I would say J goes from 1 to, 50 billion, something like that. Who knows? And then what's this? Now we have to introduce this new function, this work function, which I call Wij, which is basically saying how effective is a given person at using a given tool or doing a given job, right? If you have someone who's 5'2" and weighs 90 pounds and you give them a jackhammer, there's not much output there. They probably can't even lift it up, right? If you give someone who's 6'8" and 300 pounds and you give them the job of doing termite inspections underneath people's homes, they're not going to be able to enter the crawl space, right? So there's those kind of things. Or if you give someone who's very mathematically talented and maybe they're a really good programmer, and you turn them into a politician to give speeches, and they're probably not going to do very well, right? So we have to match up the functions in the economy with the people and their skills. So maybe a better starting point for the equation of production is something like this: a sum over all the different people, a sum over all the different tools or jobs, or however you want to look at K, and then the weighting between them showing how efficiently one person can use that tool or how efficiently that job is done by that particular person. So this WIJ, this work or efficiency matrix, measures how efficient a person is at a given job. That, of course, varies with time. So here's the other piece that's missing from those equations is time, explicit time. You are not going to be as good at a given job today as you were a year ago, 10 years ago, 20 years ago, or will be in the future, right? So your ability to do a job is going to vary with time. You might get new training, you might get hurt, you might just lose interest in something. T with time, with T, your ability, one person's ability to do one particular job or use one piece of equipment is going to vary quite a bit, right? So let's talk about how that might vary. Well, could depend on your work history, right? The longer you work at a job, the more experience you get. Hopefully, the better you get at it. And if you have a series of jobs, they may somehow, lend some more work experience to what you're doing now. So if you piloted a fishing boat for 10 years and then you got a job as a tugboat driver, your experience with the fishing boat, a piece of capital we call fishing boat, will help you with the piece of capital we call tugboat, right? So there's some work experience, and that's going to vary over all your life and over all the other possible jobs you could do. Um, this is not exactly right. We need to include the fact that not every job contributes. So the tug driver can leverage his experience as a fishing boat operator, but if he had in the past been a janitor, uh, that doesn't really help much at all with being a tugboat pilot, right? So there's going to be, I don't know, I call this the cross-training function, which relates the job you're trying to do now with all the other jobs and how relevant they are to the job you're doing, right? If you've done, maybe you were a bond trader, maybe that helped you be a better stock trader. But if you were a car dealer, maybe that doesn't help you become a better stock trader. And of course, it depends when, right? Like if you traded bonds back in the 80s and now you're trying to get a job as a stockbroker, well, you've probably forgotten most of what you learned, right? You went on, you did other things for the intervening 30 years, and now you've forgotten it all. So I have this function here called the forgetting function, which says it matters at what point in the past you had this experience as well, because you may forget, or maybe that experience has become more relevant. It's hard to tell, right? This function could be pretty much anything at all. So so this is a start on how this work matrix might be put together. And I think it's just the bare beginning of what a real model would have to contain to actually model the real world. Let's move on to output. So what is output? The Q is an output. Well, let's go a level deeper. We make a whole bunch of products, and P would be products. Those could be goods and services, haircuts and shoe shines and belts and fish or whatever it is that we're producing. And so let's just call that J. And J, again, how many products do we make? I don't know. It's, again, probably like tens of billions. Let's call it 50 billion, right? So J goes from 1 to 50 billion. And then we say how much of each product did we create? And that's the total output. Now, again, we're skipping over the issue here of you can't add 10 apples to 10 oranges and say it's 20, right? Those are two different things. And so we value things differently, right? Each person values each product differently. And so you may say like, maybe we got a whole new piece of capital last year, which is the asparagus grower, right? And we grew 50 million tons more of asparagus this year. But not everybody likes asparagus, right? And if the people who like it already have enough and nobody else wants it, then that capital doesn't add to the output of the economy, it just adds to waste, right? So here I introduce this new matrix, V, the value matrix, which is I is the individual person, J is now the output product, and there's some matching of how much output product was produced to the value that each person puts on it and some sort of sum over that to produce the total aggregate output Q. Now we can do the same argument we did with the W matrix, okay? So I don't worry too much about this, but how much you want a basket of apples is going to depend on how much other stuff you've consumed. Like, have you been eating a basket of apples every day for the past month? If so, you probably don't want any more apples. But if the last time you had apples was 2 years ago, you might really, really value some apples. Also, it depends if you've just stuffed yourself on cherry pie for the last week, you may not really feel like buying any apples. They may not have much value to you today, but then if you don't eat anything for 2 weeks, you might really, really, really want a basket of apples. So your value that you place on apples is going to vary with time. It depends on what you've consumed before. It depends on how long ago in the past that was. And you may also say, well, there's some kind of, I just like apples, and yeah, I don't really want many right now, but in general, I do like apples, So, but again, that varies with time. When you were a kid, maybe you liked Lucky Charms a lot, and maybe now you don't. So, depending on the time, your value for some individual product might go up and down. Again, uh, don't worry with the actual structure of this equation. I'm sure this is wrong, but I just want to kind of show how complex this problem is. So now we have this set of equations, right, where the total output at a time t is going to depend on the value matrix of all these people for all the products. So V is like runs from, it's a 330 million by 50 billion matrix, each of which elements is time dependent. The products that are produced are is according to the efficiency function, the capital function, the labor function. So again, this is like some sum over hundreds of millions of people working on all this kinds of capital. The efficiency function depends on all the work that you've done in the past and how closely related that work was to you and what time it was in the past, and sum up all that over all possible jobs that you might have done. And then the value matrix, on and on and on. So you have these sets of equations which contain calculus, right? Differential equations. They contain matrix math where the matrices are on the order of billions and billions of elements by billions and billions of elements. They contain time dependencies, and they contain nonlinearities where one like the function w is dependent on itself at some other time, um, multiplied by a whole bunch of other stuff and summed over a whole bunch of other stuff. Now, notice that we can never know the actual values of the V matrix. We can never really know all the values of the W matrix. We don't really know what these gamma and delta matrices are. We don't know what the C function looks like. Like none of this is knowable. I mean, we can write these things down and say, well, there's some function that says how much one job cross-trains another, but we can't quantify it. There's no way to measure that. And in fact, the C matrix really should also contain the number I, because if I cross-train in a job, I may get better than you if you cross-train at the same job, even if we're doing the same thing, right? So I just may learn better than you, and so it might depend on the person as well. So, okay, so speaking as someone who's done this kind of math in the past, this is hopeless, right? There's just no way to solve this set of equations. And you'll never do it like analytically by trying to solve the equations by, scratching your head and using a pen and paper. And it's never going to fit into a computer when your matrices are billion by a billion, right? It would take eternity to calculate. And we didn't even get to all the stuff, right? Like there's more things that are really important in the real economy. So, we've kind of matched each person to each job and say, okay, they produce some output, but that's not the way the real world works, right? Very rarely. I mean, maybe yes, there's a carpenter who has a set of tools, and if he has these tools and these wood, he can produce a chair. Okay, but that's generally not how things are done, right? People don't individually work with a single piece of capital equipment to produce one lone piece of output, right? Um, People work in teams. And who you work with, as anyone who's been out in the real world knows, has a huge impact on your productivity. If you work with people you like and trust, you do a way, way better job and produce much more output than if you work with people you hate and fear, right? Then you can produce pretty much nothing, using the same amount of labor. So the arrangement of people is incredibly important. And so is the arrangement of capital, right? Like there's not just a wood lathe out there somewhere, right? A wood lathe is in a shop with a whole bunch of other things. If you just have a factory with 50 wood lathes and no other woodworking equipment, it's going to be really hard for those carpenters to produce anything nice, just dowels, right? They're not going to be able to produce like a table. Um, so the physical arrangement of the capital, like what capital is used together and what teams are working on it, is all super hugely important to calculate the output of the economy. All right, so how would you maximize output then? You have those nasty equations and you have all this stuff. Well, so there's several tasks here. You need to optimize the W matrix. In other words, some people are good at some things, working with some forms of capital, doing certain jobs, and others are not. You need to match everybody to their quote unquote best job. Again, think of that software engineering team example. Like if people are doing the wrong jobs, the output is going to be ludicrously low, right? But once you match people to their right jobs, magic can happen and things can go up by factors of 10, 100, 1,000 easily. So how do we optimize in the real world? How is this optimized? Well, this is kind of the responsibility of the individuals, right? Like you have to know as a worker, you have to know at that what kind of jobs you're good at, what you think you would like. You have to be able to suss out the culture of a company and a team and decide whether or not that's the right place for you to work. And if it's not, you need to change your job and keep looking until you find something that really brings out your talents. If you're an employer, it's the exact same thing with hiring people. You have to look really hard for candidates and see whether their skills and personality fit the team and the mission that you have. And if not, you need to get rid of them and look for somebody else. And there's this constant back and forth between slots and workers for labor to try to optimize this W matrix. And of course, as we noted, everything changes with time. Like the optimal configuration today is not the optimal configuration next week. And so that's why people are constantly leaving their jobs and getting hired to new jobs, and everything's in flux all the time because none of this stands still. And then, given the V matrix, the value matrix, how much people like each product, which of course is undiscoverable. You can't know in a mathematical sense what that matrix looks like. But basically what this says, we need to match the output of all of our factories and companies and things to the products that people want. How do we give the most satisfaction to the most people? When people are there's hundreds of millions of them, or if you look at the whole world, billions, they all want all kinds of different things, and they change their mind minute by minute on what they want. How in the world are you going to optimize the output of the economy to satisfy those crazy people? This is what economists, at least Austrian economists, would call the entrepreneurial function, right? When you are trying to figure out what to make, how to satisfy your customers, you're acting as an entrepreneur. So by entrepreneur, I don't mean like some young kid who starts a high-tech startup and makes $1 billion. I mean, that is entrepreneurial, but it's not what we're talking about here. Talking about, using your human intuition to look around and figure out, hey, maybe if we did this, I bet our customers would like that. And this happens continuously because customers are constantly changing their tastes and their preferences, as the world changes, right? So in the real world, how do we maximize output? It's all done kind of by intuition, right? Like it's workers looking for the right job, it's entrepreneurs looking for the right combination of market and product and team, and it's a constant experiment to try to figure out what's going on. You can't know, there's no program you can run to figure this out. So how do they know if they're correct? All these people are taking these guesses like, I bet the market might like this. I bet our customers might like that. I bet this employee would work well with us. How do you know? I think this is the right job for me. How do you know? So there's no scientific objective measure. There's no econometer. There's no economic laser scanner. You can scan when a person joins a company and say, oh, this is a good use of their labor. Absolutely. They're going to produce a lot of output here. You can't figure that out, right? The feedback mechanism that we do have is called profit and loss. So if you are an entrepreneur and you arrange your company to produce things that lots of people really want, you make lots of money. That's your signal to say, hey, you're on the right path here. You're going down the right direction. Like whatever you're doing, keep doing it because people seem to like it, right? If you're an entrepreneur and you produce something, your company produces something that nobody buys, then you start losing money, and that loss is a signal to say, hey, stop what you're doing. Like you're getting colder, right? The more money you make, the world is telling you you're getting hotter, and the less money you make, the world is telling you you're getting colder. Try something else, right? If you are if you trained as a doctor and then you got a job as a janitor and you're making $8 an hour, you go, this doesn't seem right. Like that, there's not a lot of I'm not making a lot here. And then you switch to become a brain surgeon and you increase your salary to $800,000 a year, that's a signal to you like, okay, yeah, you're getting warmer, like you're doing something better here. This is a better use of your skills based on what all the customers want and what people value. You have a better use of your skills here as a brain surgeon than you did as a janitor. So in general, money in the economy will flow towards the people who pick the right job, to the employers who pick the right employees, to the companies that use the correct types of capital and equipment, and to the ones that make the right products that customers want, right? The system is not super perfect, absolutely flawless, but in general, this is how it's going to work. And so over time, as time flows on and everything changes and people change their mind and they enter the workforce and leave the workforce and equipment wears out and new equipment is built, there's this constant reshuffling of everything as people try to optimize all the new pieces. And the way they do that is by looking at where the profits are flowing. And the people who are making profits are doing something right, and the people who are making losses need to stop and try something different. So in some sense, the economy populated by actual human beings solves these equations like using it's like a cellular automata program. If you don't know what that means, don't worry about it. Using profit and loss as some kind of figure of merit, right? If you're going to talk in mathematical terms. And each little piece, each little person chugs along and does what they think is the best thing for themselves and for their customers in order to maximize and the way they know if they're succeeding is by maximizing the profit that they're making. Okay, so this is more like the complexity of the real economy. And there's two big pieces we added in here. That things change with time. Actually, there's several things we added in here. Things change with time. Different people are good at different things. There's heterogeneous capital and there's heterogeneous labor and there's heterogeneous products, and people are good at certain things and not good at others. People value certain things and they don't value others, and all of that changes with time. And when you try to include that, you start to get equations like this. I'm sure like these are wrong mathematically and probably need to be way more complex when you start to include group effects, and also where things are located is also really important, right? If someone's doing awesome acting that you love or opera, but they're in South Africa and you're in Canada, it doesn't really add to your life enjoyment, right? Because you can't see them. So I'm going to submit again that this sort of equation where you have aggregate output is some function of aggregate labor and aggregate capital is so misleading and so naive as to be useless and even dangerous. It leads you to conclusions that are completely wrong and leaves out all the important parts of the economy that we just talked about. And for those of you who've actually done a job or ever bought or sold something, you'll recognize that everything I said is true, right? All those pieces that I laid out, it's like, yeah, that's right. Like this matters, that matters. Those things do change. Different people are different. This sort of model of the economy doesn't include anything that's important. And this is why most of what modern day mainstream economists say sounds so ludicrous, because it is ludicrous. They're working off models like this that don't capture the actual complexity of the or the humanness of the real economy. Remember, this is Ken DeLong, author of the Economic Comic, reminding you to don't listen to these crazy guys. Form your own opinions. Think for yourself, and use your own brain to decide what is true and what is not true. And if you'll do that, I'll see you again on the next video. Hey guys, if you want to understand more about economics, but you're just tired of the jargon and the technobabble of professional economists and media pundits, then check out my book, The Economic Comic, which is available on Amazon. There you can learn some of the concepts of economics through comics. Thanks for listening.